we'll see another method of solving initial value problem of first order ODE. Many a times this method is used when the previously discussed methods, all of them fail. So this is called Picard's iteration method. So this was given by Picard. So the aim of this method is to solve a first order ODE, is the initial value problem of the following type: y dash is equal to f of x comma y and y of x0 is equal to y0. Y of x0 is equal to y0 is the initial condition of the differential equation y dash is equal to f of x comma y. Now we can apply fundamental theorem of calculus to write it in this following way. So by fundamental theorem of calculus, this integration we get y of x minus y of x naught is equal to integration from x naught to x of the function f t yt bracket close dt. So this integration is performed with respect to the variable t. X naught is the point at which the initial condition is given and the value at x naught is y naught. It is same as y x naught. So we rearrange and it is yx is equal to y naught plus integration x naught to x f of t comma yt dt. Note that they are equivalent forms, so any solution of 2 is a solution of 3 also. So we can simply solve the equation 3. Now this equation 3 we are going to solve in an iterative way. What we do is, in this equation, in place of yt, we substitute the number y naught that we obtained from the initial condition. And when we put y naught here and perform this integration and add y naught to it, whatever function we get, we call it y1 of x. That is the first iteration. After we finish the first iteration, now this y1 we will substitute in this equation 3 in the place of yt. So we are substituting y1 in the place of yt, and again we can perform this integration, add y naught, and whatever we get, that we call y2x. That is the second iteration. The third step will be to substitute y2 in place of yt here, perform this integration, add y naught, and the resultant function will be called y3t, and so on. Like that we will get y and t. So this is the y1t. Then after substituting this y1x here and performing integration, we get y2t, and like this you keep on going till you get y and x. The general formula is equal to y naught plus integration from x naught to x f of t comma y n minus 1 t bracket close dt. These are the iteration steps that you have to perform. So under the assumptions of the existence uniqueness theorem, this sequence of approximation converges to a solution yx. Recall what are the assumptions of the existence uniqueness theorem. The assumptions of the existence uniqueness theorem is that f x comma y should be a continuous function and it should satisfy Lipschitz condition with respect to the variable y. Let us see the initial value problem statement once again. So here is the statement. We need the continuity of fxy and we need if this condition to be satisfied. Note that the existence uniqueness theorem was given by Pinot and Picard. Pinot had proved the existence theorem, and later Picard had proved existence as well as uniqueness. And part of the proof of this uniqueness theorem is through Picard's iteration, which we are discussing now. So this is the Picard iteration that we just now saw, and it turns out that under the assumptions of the existence uniqueness theorem, in certain interval, the iterations converge. The sequence of approximations converge to the solution of the differential equation. So the solution yx is given by the limit as n tends to infinity yn xn, where yn xn, they are all functions. This is a sequence of functions, and this sequence of functions converge to another sequence, to another function. This sequence of function converges to another function, and that function is the solution of the given initial value problem of first order ODE. So we'll see an example of solving using Picard's method. So the problem is y dash is equal to xy, and initial condition is y naught equal to x1. Of course, this equation can be solved directly also, because this is separable ODE, and Picard iteration is mostly used when we cannot solve it by direct method. But just to illustrate the method, we take a simple equation which can be solved by other methods also, and then we will compare whether both the solutions are same or not. Obviously, the solution should be same. So the first integral equation, if we integrate this equation with the initial, if you integrate this ordinary differential equation with this initial condition, what you get is yx is equal to 1 plus integration of x naught to x t yt dt. The successive iterations are as follows. From this equation, if we substitute in place of yt, if we substitute y naught, so y naught here, then you get the first iteration y1x. So here the y naught is 1. So substitute 1 in place of yt. So this is what you get, because here the y naught appears here as well as the y naught appears here. Both the places we put 1. So we get 1 plus integration 0 to x, because 0 is x naught, t dot 1 dt. So t multiplied by 1. This is our y1x. So what we get is 1 here, and this is integration of t from 0 to x. So integration of t is t square by 2, and when you put the limits, we get x square by 2. So this is y1x. Now next step is this y1x has to be substituted in place of this y here, and you have to convert that into y1t here. So it will come here as t times 1 plus t square by 2, like what is written here, t times 1 plus t square by 2. When you integrate that 0 to x, because 0 is x naught, plus 1, which is y naught, that will give you second iteration, that is y2x. So this one integration we get 1 plus, this will give t square by 2, and this will give t raised to 4 by 2 into 4. And when you substitute the limit, we get 1 plus t square by 2 plus t raised to 4 divided by 2.4. If you keep on computing the iterations, the nth iteration will be 1 plus x square by 2 plus this, you see, this 1 and 2 can be taken out, and then it will be 2 square. So it is 2 factorial times 2 square. So we can write it as 1 by 2 factorial times x square by 2 whole square plus so on up to 1 plus n factorial times x square by 2 whole raised to n. So whatever power series this iteration gives us, we can try to arrange it so that we get a known sequence or something in terms of known sequence. For example, here we were arranging the term, we were trying to organize the term in such a way that they have something to do with the exponential function, the power series expansion of the exponential function. So from this solution, it is clear that the solution is the exponential function raised to x square by 2. So this, when you take limit, it is nothing but exponential function, and in place of variable you have x square by 2. So e raised to x square by 2 is the solution that we get by Picard's iteration. Now if you solve this equation by direct method, you are also going to get the same solution, because this is variable separable form. This can be written as dy by y is equal to x dx. So we get ln mod y is equal to x square by 2, which is same as e is equal to y is equal to e raised to x square by 2. So we get by direct method as well as by Picard's method the same solution for this initial value problem. Now some comments which you can try as an exercise. Does uniform continuity imply Lipschitz continuity? You must have learned uniform continuity in your previous calculus course. So try to pause the video and try to answer this question. So the answer is no. We can take a uniformly continuous function, namely fx is equal to root x when x belongs to this interval 0 to 2. Any continuous function on a bounded interval is uniformly continuous. Since this fx is equal to root x is a continuous function and we are taking a bounded interval, it is uniformly continuous. But we know that it is not Lipschitz continuous because we have seen this kind of example before in our lecture. The next question is about orthogonal trajectories. The value of n such that the curves x raised to n plus y raised to n equal to c are orthogonal trajectories of the family this family is y is equal to x by 1 minus kx, where k is constant. So we have to take this family and compute its orthogonal trajectories and find out that what is the value of n. Orthogonal trajectories are going to be of this form with particular value of n. So how do you proceed? First, you recall what you did previously. You have to find the differential equation corresponding to this family of curves. Pause the video and try to answer this question. Okay, so first consider this family of curves and find the differential equation. So when you compute this, so dy by dx will compute. So you know how to differentiate this particular thing. There will be square of this, and then whatever form it comes, when you rearrange it and try to eliminate the constant k, the differential equation of this family of curves will be dy by dx is equal to y by x square. You can show that. So if this is the differential equation of the given family of curve, the differential equation of the orthogonal trajectories will be dy by dx is equal to minus bracket y by x by y square. So the differential equation of the orthogonal trajectory will be dy by dx is equal to minus bracket x by y square. So that differential equation, when you solve, you will get x cube plus y cube is equal to c. So that means the value of n is equal to 3.